which is called the value of stability. So these are the stable isotopes. These are the isotopes that form the world that we know. And all the rest of them that are indicated here are radioactive. And various colors means different types of radioactivities. What is the origin of these isotopes? It's a very complicated thing, but in principle, we can these isotopes put into 6 categories. And first are primordial isotopes that were produced by primordial nucleosynthesis very soon after the Big Bang, up to 20 minutes, and that's hydrogen, helium, and a small fraction of lithium. Then the stellar nucleosynthesis, the various stages of the life of the star, produce different elements through different processes. This can produce elements between carbon and bismuth. We'll see example of how the carbon is produced in the stars. Supernova explosions and the neutron stars collisions are responsible for neutron-rich stable isotopes and for uranium and thorium. Then we have nuclear decay that very well known are natural decay chains of uranium and thorium that are producing the elements that occurs on the Earth. For example, radon gas, which is very important from point of view of new buildings and especially cellars. 3 elements, lithium, beryllium, and boron, were created by interactions of the cosmic radiation in interstellar space. And then we have man-made elements, but some of them are known to exist in the universe. That's examples of technetium and promethium that do not exist on Earth, but their lines were discovered in some of the stars. And then we have a whole variety of super heavy elements going to element 118, which was quite recently discovered in Dubna. And understanding of the isotopes is therefore important for us to understand our own origin. So, and if you want to learn something more about the processes that create the elements, I refer to YouTube. Where is my lecture? It's in Slovak. So, which was made just before the start of a pandemic with the collaboration between Slovak Academy of Sciences, Comenius University, and Slovak University of Technology. So it's called Tabula or Blackboard. So, and that's in this lecture I explain step by step how the Mendeleev table appeared. Okay, very briefly on the applications of isotopes. So we all know energy production. I don't need to spend much time on it. However, the nuclear power is considered as green power. Even the European Commission finally gave this statement. So now officially nuclear power is green power. So nuclear medicine is extremely important because, for example, approximately 30 million of patients per year undergo diagnosis procedure using 99 technetium isotope. And then we have therapy of tumors or positron emission tomography. I also refer to recent article in Nature that proposes a new version of positron emission tomography based on the quantum entanglement, but still it needs a radioactive isotope. And there are many applications then in archaeology, geology, or national security application. Okay, so what is doing atomic nucleus today? So presently, there are known something like 3,500 isotopes. We have 118 elements, starting with hydrogen, and the last one that is known is oganesson. Very recently got the name after Yuri Oganessian, who discovered it in Dubna. Out of these 3,500 isotopes, only approximately 250 isotopes are stable. The question is what we call stable, whether they are stable or are long-lived. For example, bismuth 209, which is the bismuth metal, is well known, but it's radioactive, very, very slightly radioactive, with a half-life of 10 to 19 years, which is 9 orders of magnitude longer than the age of the universe. So we can call it stable, but it's not really stable. So the question is how many if there really are stable nuclei, probably not. There are few elements without stable isotopes. Everything what is heavier than uranium doesn't have a stable isotope. Or sorry, then lead, even the uranium is not stable. But we have two other elements, the technetium and promethium, that do not have a stable isotopes. And how we can learn something about the structure of atomic nuclei, we can address their structure via their excited states. And in these 3,500 isotopes, there are known approximately 176,000 of excited states that are known. What are the characteristics of excited states, which I will be using in this presentation? First is excitation energy, which is relatively easy to measure. Not always, but in most of the cases, it's easiest to think what you can measure. There are two excited states known below 1 keV. One is 229 thorium, which is only 8.9 electron volt, and it may have very serious applications in the future because of this very low energy. And the second is notoriously known uranium-235, which is 76 electron volts. However, most of excitations occur at hundreds of keV. So this is our scale that we will be using will be hundreds of kilo electron volts. Highest known excitations are known at few tens of mega electron volts. Second is a lifetime of excited states, and it goes from tens of femtoseconds up to 10 to 15 years. So I don't know any other quantity with such huge range outside of theoretical cosmology. So it's a really big scale. A very interesting case is tantalum-180, which is very rare isotope, but it's the only one that exists on Earth in excited states, because this is 10 to 15 years, so we can consider it stable. So this isotope is radioactive in the ground state, however, is stable in its excited state. And if you take 1 cubic centimeter of pure tantalum metal, it stores about 75 kilojoule of energy in nuclei of these isotopes. And very, very slowly it releases this energy in the form of gamma rays or conversion electrons. Then the excitation modes of these excited states, most common is the emission of gamma rays. But then there are higher order processes like internal conversion, internal pair creation, or two-photon emission. So I won't be discussing them today. So we will be strictly speaking only about the gamma rays today. Then you can have a radioactive process. You can have alpha decay coming not from the ground state, but from excited states. And there are also no excited states that spontaneously fission. And the most important characteristics of the excited state is the spin and the parity of the wave function. Okay, how we can excite atomic nucleus? First, we can take the nuclear reaction. Usually after the reaction like fusion or radioactive capture, transfer reaction, the resulting nucleus is highly excited and emits gamma rays. Then what we can do the nuclear decay. If one nucleus decays to another one, very frequently the daughter nucleus is in excited states. And also if you make the nuclear fission, you split the nucleus into 2 or 3 or 4, but these fragments are highly excited and emit the gamma rays. Other processes is that you start from the bottom, from the ground state. You can either Coulomb excite the nucleus or via some inelastic scattering processes. For example, you let the high energy gamma rays to scatter on the nucleus and you can excite it and then measure the excitation. Very important property of atomic nuclei is pairing. So they create pairs of proton-proton and neutron-neutron pairs. This is different from atomic shell, where you put the electrons into orbitals following these Hund rules, not in nuclei. So if you take even nucleus, this means nucleus with even number protons and even number neutrons, they have zero spin in the ground state because all the spins cancel out. And it has several results. And for example, that doubly odd nuclei are rarely stable. I think there are only 4 stable isotopes with odd number of protons at odd number of neutrons. And elements with even proton number are more abundant in the universe and typically have more stable isotopes. So if you look to this, I point to logarithmic scale here. So this is proton number, and this is relative abundance. So you see that most abundant element in the universe is hydrogen, then helium, and then you see question.
Akin, yes, I have question.
Yes.
Even nuclei don't have spin. I don't know any quantum object which exists without the spin. How to understand it?
It's zero spin. Spin is zero.
Zero spin. So
Okay.
they have spin, but
they have, okay. It's
zero.
Yeah. I should call it a zero spin.
Yeah.
Yeah. Okay. So, but you see the staggering between. So they are far more abundant and typically have more stable isotopes. So if you take piece of tin has, I believe, 10 stable isotopes. But if you take gold has only 1 stable isotope because it's all the Z. Okay, so then what you can do if you measure the energy that you need to separate, 2 neutrons, you see markedly jumps at n equals 20, 28, 50, 82, and 126. And these are so-called magic numbers, and these are analogs with the noble gases in chemistry, and the magic nuclei have increased stability, and even the doubly magic nuclei have both protons and neutrons closed shell. So I will show a little bit later what's the microscopic origin of these magic numbers, but how the magic numbers are reflected in excited state. So this graph shows the excitation energy of the excited 2+ state in even nuclei. Even nuclei have a 0+ ground state because of a pairing, and most of them, not all, but most of them, the first excited state is a 2+. There are various possibilities how to get it. But you see, this is example of tin 132, which is 50 protons and 82 neutrons, doubly magic nucleus. So the excitation energy goes very high up. And still, if you stay at the magic proton or magic neutron number, it's still quite high. But if you go far away from both, it's going rapidly down. So this magicity is reflected even in the thing which is quite easy to measure, energy of the first 2+ state. And then what you can do, you can search for 4+ state, and you can calculate the ratio between excitation energies, and it comes close to 3.33, which is a limit of the rotational model. So the nuclei have rotational bands. We know the rotations of molecules. So also the nuclei have them, which means they must be deformed. So now the question is, are nuclei deformed or are they spherical? And the answer is indeed, some of the nuclei are deformed, as it is shown here. So this is the quadrupole moment in some strange units. And you see the spherical nucleus should have it 0. And there are nuclei around the 0, and these are those that have the magic numbers inside. As soon as you go between the magic numbers, you strongly deviate from the spherical shape. So you have either prolate shape or oblate shape of the nucleus. So, and the microscopic explanation of magic numbers comes from shell model. So if you take the Hamiltonian with the nuclear potential and the most realistic is a Wood-Saxon potential. And if you include the spin orbital term, what Maria Geppert-Mayer and Hans Jensen did and got a Nobel Prize for it, you describe the magic numbers as a closed shell. So it's a big indiscrepancy between orbitals. So you you just close the shell as you do in noble gases. So the theory does not have the consensus yet where the next proton magic number should be. Either it is 114 or 120 or 126. And that's the main reason of this hunt for super heavy elements, because they can form island of the stability. And the problem is that we have the nuclei up to 118, but we so far don't have right isotopes. They are still lacking approximately 10 neutrons. So, and now the question is, if the magic numbers are preserved as soon as we go to extreme with neutron rich or neutron deficient isotopes. Okay, so what happens if we, because this is a spherical potential. What happens if we introduce the deformation? And the first, like a model description, did Sven-Gösta Nilsson in 1955, who introduced the deformed potential, and this is the solution then. So you have deformation parameter, which is this epsilon, which can be either positive or negative for either prolate or oblate nuclei. And this is then these orbitals start to move away. So you spread them into so-called Nilsson orbitals. So Sven-Gösta Nilsson died relatively young, so he never got the Nobel Prize. However, his collaborators, Ben Mottelson and Oe Bohr, who was the son of famous Niels Bohr, got the Nobel Prize for this work. And but if the nuclei are deformed, why they should be axially symmetric? And this is what Mottelson and Bohr introduced. Is the different parameterization. So if we take the shape of the nucleus described like this, which is, by the way, exactly the same way how the shape of the Earth is described, and presently is known, I don't know, but certainly more than 1,000 members is known. And if you want to get the precision better, the octupole, the lambda equals 3 on Earth's surface means something like 80 meters. So if you want to describe it better than 80 meters, you need the third term of this. So today we will be focusing or restricted only to quadrupole deformations. So we will not go with lambda higher than 2. So of course the nuclei have an octupole degree of freedom. There is known static octupole deformation. Nobody has seen yet the static hexadecapole deformation. However, there is known strength of hexadecapole transitions in few nuclei. So, and we will use the polar coordinates for this. So beta and gamma, and this is the convention that the nuclei that are axially symmetric have gamma equals 0 or equal to 60 degrees. Anything between is a triaxial, which means the nucleus is not anymore rotational ellipsoid. So, and the beta is elongation of this, let's call it ellipsoid. The best way how we can or not maybe one of the ways how we can understand to this deformation is via particle core coupling. So it's very difficult, or it's impossible now to calculate these, let's say, 200 nucleons interacting with all interactions for using ab initio models. So how we can simplify this problem is that we take particle core coupling, that we take odd nucleus when odd nucleus acts as a spectator, and we couple it to even core, and we are investigating then only the spectrum of just one particle, and from impossible we can come to the model that is solvable. So, and I plotted the three extremes here. A means spherical nucleus with beta equals 0, and this is how the spectrum would look like of hot particle. So and this is other extreme is a prolate nucleus and oblate nucleus, and you see the pattern is different, and whatever is here is triaxial. And okay, this is just how the basic model done by Meyer-Terween, and later it was extended by Ingemar Ragnarsson and Paul Sams. And interestingly, that this article at some point stops. So I did a little bit of archaeology, what happened to these guys, and Meyer-Terween went to the theory of fusion reactors, and he is still publishing in this area. And Paul Sams became dean and never came back to science. And Ingemar Ragnarsson is still active at the University of Lund. So this is the solution then. I know it's a little bit complicated. So this is the gamma parameter, and the beta is fixed. And these are excited states. So if we take prolate nucleus, it has this kind of spectrum, triaxial in the center, this, and oblate like this. And you see major difference, let's say 3½ minus, how it is going up. 7½ minus is strongly sensitive to this. So what you can do, if you measure these excited states, this model can tell you where in this triaxial plane you are. What is your gamma and what is your beta? And this is something that we don't have yet, is just the empirics. So which isotopes have what shape, and this is the way how to probe it. So these deformation parameters we can get from excited spectrum. What we can use also are the transitions in atomic nuclei. So if we have transition from initial state to the final state, so there is selection rule for the spin. So this is spin of initial state, this is spin of final state, and also the parity must fulfill the state. And this will tell us what kind of transition it is, because electric transitions change the distribution of electric charge, and the magnetic transitions change of electric currents in nuclei. So I have example here. Let's say if you have a 3½ plus state to 1½ plus state, so the spin selection rules tells us this. So parity selection rules tell us that it must be magnetic dipole or electric quadrupole transition. And if we know the character of the transition, so then we can investigate its probability. If we know the lifetime and if we know the gamma ray energy, then there is a reduced transition probability given as this. So the wave functions are coming here. So if you know the lifetime and gamma ray energy, you can directly investigate the wave function. And this is something that is calculated via modern models of atomic nuclei. So if you really want to probe the structure, you need to know lifetime and E gamma. And your nuclear physics is here. There are many articles around us that put this equals to 1 and just use the lifetime to elucidate the multipolarity. So the multipolarity lambda is the L, which I had here. So if it is quadrupole transition, this lambda equals to 2. So then there is factor E gamma to 5, so which is very, very strong. So this controls the decay probability. So, but you have to be very careful because your nuclear physics is here and not here. This is what you measure, but you need to know this lambda. And for these B values, so-called Weisskopf units are used. So as an approximation, I would call it, it's like a original definition of kilogram. So there is one certain transition in one certain model said this is one Weisskopf unit, and everything is related to that. So we will be dealing with quadrupole transitions. So they have typically between 1 and 35 Weisskopf units. So very important thing is two-state mixing in atomic nuclei, and I know that we have colleagues that investigated a lot the two-state mixing recently, and it's extremely important. So if you have a two states with the same spin and the parity, so you start to mix their wave function, and their excitation energy is perturbed. So if you solve this Hamiltonian, you get this, and it influences the decay probability, as we will see. It's a key thing for us, is a two-state mixing. Well, okay, we discussed the excited states and the deformation, and the question is, are all the excited states the same? Answer is no. And we have example of oxygen 16, which is spherical in the ground state. It's doubly magic nucleus. Doubly magic nuclei are, or we believe that they are spherical in the ground state. However, there are rotational bands seen. And as I said, that for the rotational band, you need to have a deformation. And indeed, there are many signatures. These are these Weisskopf units. Value 60 is quite high. I didn't tell it here. You see that for the deformed nuclei like californium, they are high, and for the spherical nuclei, they are low. So it's one of the indication of the deformation are high, Be2 values. So oxygen 16 is spherical in the ground state, but has deformed excited state. And the same you can observe in other doubly magic nuclei in calcium 40 or nickel 56. This is called shape coexistence, and these are the regions of the table of isotopes where it was observed. So, and we will be dealing today with these nuclei. And is the shape coexistence for us important? The answer is absolutely, because otherwise we would not be here. And the reason is here that how you can produce carbon 12 in a star. So first, if you fuse two alpha particles, you get beryllium 8. But the beryllium 8 exists only for such short time. It's not bound nucleus. But if you have a high flux enough alpha particles, this time can be enough to capture the third one and get the carbon 12. And we are very lucky that the carbon 12 has excited state exactly at right energy that corresponds to masses of these free alpha particles. And thanks to this, the cross section has a resonance at the right energy. And in 0.04% cases, you create carbon 12. In the rest, it decays back to free alpha particles. Without this excited state at right energy, this would be many orders of magnitude smaller number, and you would never produce carbon 12 in the universe. So this state out of this 176,000 is the only one that I know that has name. It's a Hoyle state by Fred Hoyle, who proposed it. And by the way, Fred Hoyle is the person who was the first one to use the term Big Bang. So if you look around now, and everything what you see, including yourself, except of hydrogen, was once a Hoyle state. Every atom went through the Hoyle state, because as soon as you produce carbon 12, you can produce all the heavier elements. Without them, the universe would be just carbon, helium and hydrogen. So, and it's strongly deformed, and it is the deformation that makes the excitation energy just right to produce carbon 12. So without the shape coexistence, we would not be here today. Okay, so now I finally come to the research program at the Department of Nuclear Physics, and our focus is on odd mass gold isotopes. Why gold? So the reason is that there are strongly and weakly deformed configuration that coexist at low excitation energies. Second reason is that excited states are easily accessible with various experimental techniques that are available at CERN or in cyclotron laboratories. It has really this advantage that, for example, mercury produces with the beta decay, produces the gold. And it's easy to produce mercury beams at this order. For example, it's impossible to produce platinum because of the different chemical properties. And these isotopes are complicated enough to get a lot of information at the same time, but are not overcomplicated that we would be lost. And at the same time, they can deliver us very rich spectrum of various configuration. And why odd mass? Because I said that odd mass nucleus can bring us information of both axial and triaxial. Okay, so what kind of orbitals are involved? So this unpaired proton can be in one of these orbitals or also in these above Z equals 82. And this each configuration that we here form, we can understand it that each of them has its own Hilbert space and lives in that Hilbert space, and very rarely they communicate with each other. So, and in reality, it is that the transitions between these different families are very rare and often become isomeric. So isomeric means long-lived. So you have excited states, let's say with 2 microseconds half-life, which is extremely long compared to other excited states in these nuclei. So where we run these experiments, so I would say main experimental place is CERN Isolde, and then the University of Jyväskylä, the cyclotron laboratory, and we did some experiments also at Temba Labs in Cape Town, South Africa. However, today I will strictly focus only to what we have done in Jyväskylä. Okay, so this is, I know, a little bit complicated picture, which even you cannot read it, but I'm sorry it's so big that I need to have it as a big poster in my office. But this is the systematics of excited states in gold nuclei. So the stable isotope is here. So, and we are moving towards a neutron deficient, and these different colors are those different families, which I said of the configurations. But the important thing is that all this is our work over the past 10 years. So our knowledge when we started with this program ended here. So we either discovered most of these states or reinterpreted existing data and systematized this. So you see this very interesting parabola. There is a reason why it makes a parabola. So, and it's extremely deformed configuration. So, okay, so what we have done or what we are doing in Jyväskylä, so over past 10 years, we measured in total for 24 days of beam time that we got, and we produced 179 gold and 177 gold via reaction was 82 krypton was the beam impinging the ruthenium 100 isotopic target, producing 179 gold, or we use the strontium beam on the molybdenum target to produce 177 gold. And so the target is here inside of the Eurogam array, which is the array of approximately 100 germanium detectors of gamma rays. Then it flies through the separator into the focal plane, where we use so-called tagging technique. So it's better here seen. So the beam comes to the target, which is hits the isotopic target, and you produce the isotope of interest, and it emits the gamma rays, which are detected here. So most of the gamma rays are emitted when still the nucleus is inside of the target. Then it flies to the recoil separator, which is at the core of it is a dipole chamber, dipole magnet, which separates the primary beam, and the products of the reactions are transported via focusing quadrupoles into the focal plane, and then you implant it into the silicon detector, and you wait for the alpha decay. And as soon as you detect such pair, like you have implantation and then alpha decay from the same spot of the position sensitive detector, you look back in time in the data analysis what was happening in the target, because you know what's the flight time through the separator. And like this, you can pick up the gamma rays which originate from each particular isotope, because with these reactions, you not necessarily produce only this. You produce, let's say, 179 mercury also. And to get rid of these contaminants, you can use this so-called tagging technique. And Okay, this is the result. So these are our spectra that are relatively clean, and these lines are the transitions between excited states. And let's say within 14 days of measurement, you have only 300 events. So it's we are talking about rare isotopes here. Okay, so this is our recent result, which we published in Physics Letters B, which is a special journal for nuclear and particle physics, where important results in nuclear and particle physics are published. For example, this is the journal where in the past was for the first time published the discovery of a Higgs boson by Atlas and CMS collaborations. So, and these are the level schemes that we measured. So these are excited states of a nucleus, and these are the transitions in between. And this is the difference between 179 and 177 gold. If you look to the figure, it looks quite similar, that you start from here, you go via cascade, then you turn to the right and get somehow to the ground state. It's very similar also here. And if you read the spins and the parities, they are the same. Very, very similar nuclei, with one difference, that this one decays to the ground state, while here this decay does not exist. This path does not exist. Also, we had much higher statistics for this nucleus, and we excluded to certain level the existence of this transition, while here it's 70% goes. And we know from experiments at ISOLDE at CERN that these ground states are spherical, and from the structure of excited states we know that these structures are deformed here. So here it appears that this is deformed, so it prefers to decay between deformed. Nuclei do not like decay from deformed to spherical. It's always these transitions are slow. This is happening here, and you see this is lifetime of 326 nanoseconds. So why here it suddenly happens and so strongly? Why 70% goes to the spherical state? Our interpretation is that there is mixing, that this wave function is not pure, because it mixes with the 9.5 plus state, which must be around. We haven't seen it in experiment, but the only explanation is that as soon as we introduce the mixing, we completely reproduce experimental data. Without mixing, it does not happen. Why it does not happen here? It's not clear. One possibility that mixing is much weaker because these 9.5 plus states are far away, but it also does not happen anywhere else around, which means that this must be completely new configuration, which is absolutely unexpected. To elucidate this, we still need far more data than we have. Other issue is the so-called strongly coupled band, strongly deformed configuration, which on the first side you see that it's different than in 187 gold. So they are 10 neutrons apart. However, if you remember the parabola, that was the idea of the experiment that we proposed. We wanted to prove that these two nuclei should be similar according to knowledge what we had about the nuclear structure of these isotopes. They really should be like a mirror. And also for the weakly deformed structure, it works. If you look here, it looks quite similar. Like this corresponds to that, this corresponds to that. Then you have this, which is here this, then you have this and this. Also the energies are slightly different, but not really big difference between them. However, if you look to heavy gold, you don't see anything like this. And the lifetimes measurement done by our colleagues, they measured the beta, which is 0.4, which means extremely deformed configuration. really, it's nearly so-called super deformation. So I don't know if Andre has, oh, Andre is present. He's expert on the super deformation. So this is nearly on this, where we start to speak about super deformation, and it should not exist at such low excitation energy. As far as I know, it was never observed below 1 MeV excitation. And what exactly are these configurations is not clear. However, we proposed more experiments to elucidate it. And one more surprising result appeared, which is unpublished. So I'm showing now unpublished data. So we've discovered a new island of nuclear isomerism, which means long-lived states. And they give us access to a lot of information. And it's here, let's say I have here 4 quantities. First is the difference of excitation energy, then magnetic moment, and then BM1 and BE2 in Weisskopf units. And with the straight lines is what we measured, and this is the error bar. And you see the agreement between model and the measurement is the best at around 30 degrees. So these nuclei are terribly triaxial, and we need to avoid speaking in the terms of axial symmetrical models. They will just not work properly in this case. Okay, so let me come to conclusion. So our goal was, or still is, to study the systematics of excited states. But in addition to this systematic work, we found new surprising results, which we did not expect and could be reached only because of the high quality of experimental data that I was proposing long experiments. And the underlying mechanisms are not understood yet, and we need far more data sets. However, we attracted the interest, for example, of the nuclear theory group from Bordeaux and from Brussels, with our dear friend and colleague Paul-Henri Heenen, who unfortunately passed away 2 years ago. So, what is important, we proposed 2 new experiments in 2020, and we got 4 days of beam time at Isolde facility and 14 more days of beam time in Finland, which is quite a long measurement. And both require development of new methodologies, which can be done in laboratory in Piestany, the same as we did for Isolde, where we are running with our own detector. So the standard detection system, which is used in Jyväskylä, cannot be used for this experiment. And if that will work, we should be able to get at least 1 order of magnitude more data at the same time than with the existing setup. And what is under preparation is a program of lifetimes, how to measure these femtosecond lifetimes. It cannot be done with detectors or with electronics. It must be done via Doppler effect. So, okay, and I have still few more minutes, so I will come what I have skipped. A few words about our author lists, because they are very often discussed, that we have quite a huge research team. And for example, as it is seen here. So what are the rules for this? So for the first the beam time is granted by Program Advisory Committee of the laboratory, which is international, and it's very, very strict. And why it needs to be strict? Because the cost of the beam times are covered by the laboratory. And I have exactly no idea, but in Darmstadt, there were always, was Sigurd Hoffmann telling me something about several thousands of euros per hour, if it includes the salaries of all the people that need to be involved. So it's somewhere there between hundreds and very few thousands. So if you measure for 14 days around the clock, you can estimate that it's quite a lot of money. So that's why they have to be very careful to what they invest this money. So it's a kind of a project. So it's like to get the grant, but you don't get it in the money, and you get it in the beam time. So, and then there is fundamental rule that all the members of local group are automatically co-authors of any paper that is measured there, And the reason is they make the laboratory running. They take care about it, and they really keep it working. And without their work, this would not be possible. You can agree or disagree on this, but you cannot avoid this. So that's how immediately we get quite a huge author list. And then you need to bring many people to run experiment, because you are running for 2 weeks around the clock. You need to take care all the time with the 2 people taking care. And the data analysis is very time consuming. Typically, we are getting like 5 terabytes of the data per week. So, and that's why it takes several years really to calibrate each channel of electronics. Sometimes we invite the theory group to help us with the interpretation of the data. So at the end, you get quite a huge author list, many collaborating institutions, but that's the only way how this kind of experiments can be done today. So this is really example of a big international collaboration. So and now the most important thing, so it's just to thank to all the collaborators from the Department of Nuclear Physics. So this is of course not the present Department of Nuclear Physics. Those in italics are not anymore working with us. Most of them were just the students. Some of them did their thesis with us. Some of them just passed by for shorter or longer time, but still it's quite long. Plus, we had many summer students from various countries, so it's a big pleasure to work with these people, and it was also big pleasure for me to chair Department of Nuclear Physics for almost 8 years, and my term will finish in 12 days from today. So this is for me. It's the most important issue on the research are the people. So, and this is all what I wanted to say, and thank you for your attention.
Thank you very much. So please, now we have time for discussion, questions or comments to the speakers. So please, you can ask.
Môžem, Martin, ja?
Môžeš, Jan.
Vieš čo, mňa by zaujímalo takú vec, že vy robíte teda experiment a že teda v podstate, že akým spôsobom sa tá teória tam vyvíja, že či vlastne tam sú nejaké také aj, alebo ty si hovoril niečo, tam boli nejaké minulosti, že či sa tu nejak počíta na počítačoch, alebo vlastne, že akým spôsobom, lebo mne to príde strašne podobnej chémii. Vieš, že v podstate máme proste nejaké elementy v periodickej tabuľke a vieme v podstate spočítať nejakými modelmi, ja neviem, spektra atómov alebo nejaké zúčeniny, že akým spôsobom vlastne funguje tá teória tam, či to je veľmi podobné, že máš nejakú koreláciu a tak ďalej, hej, že ako to vlastne je.
Ako tá jadrová fyzika je v porovnaní sa, ako ty to ideš na to správne, prirovnávaš to správne, ale máš jeden problém a to je, že to jadro má tie nukleóny po A ti interagujú všetkými interakciami. Teda akože na gravitačnú môžeme zanedbať. A druhá vec je, keď si vezmeš atómový obal, máš jadro, ktoré ti definuje nejaký potenciál a máš tie elektróny. Kdežto to jadro samotné, ono nemá nič v strede. Ono si je samé o sebe, si je stredom. Takže momentálne by som povedal, jadrová teória je pomerne dosť za experimentom.
Aha, rozumiem. Čiže vlastne...
Existuje množstvo prístupov, ktoré môžeš ako začať treba vrstvovým modelom, potom sú, ja neviem, nejaké také veľmi široké pole modelov stredného poľa. No, ako každý funguje ako keby dobre v nejakej oblasti a v nejakej oblasti javov. No a trebárs tuto problém u nás je, ja to, čo používam, ako tieto výpočty robíme my, sami, ale teda ja teda nie som ani náhodou teoretik.
Ja rozumiem.
Ale toto v podstate ani nie je model. To je, ja by som povedal, to je také nulté priblíženie, ktoré ti ale dáva istú predstavu o tom, že čo sa tam vlastne deje. Určitá také navigovanie dát. A to je to, čo my potrebujeme. A ja si myslím, že náš najväčší problém je v tom, že my síce máme 3,5 tisíca izotopov, ale to, čo som ukázal, tú veľkú systematiku, tak s výnimkou toho, čo sme spravili v zlate, tak snáď niekde v oblasti cínov je urobené niečo podobné a v mnohom nie je systematizovaná.
Aha, rozumiem. Čiže dát je málo na to, aby vytvoril niekto nejaký veľmi rozumný model, alebo neviem, ako to nazvať.
Ja by som to prirovnal v podstate k botanike za čias, keď Karla Linného, že ty, aby si mohol vytvoriť systém, tak najprv musíš mať dostatočne dobre popísaný dostatočný počet druhov.
To je jasné, áno.
A to je určitá domáca úloha, ktorú viac menej my musíme spraviť a my sme s tým začali v podstate že ideme systematicky a narazili sme tuto, ich mám tým oranžovým, na štruktúry, ktoré jednoducho nemajú precedens v tých jadrách. A teraz v podstate ako keby sme išli naspäť a oni sa niekde musia objaviť na excitačnej energii inej, v tých iných jadrách, lebo oni sa ako tieto štruktúry v jadrách sa neobjavujú akože odnikiaľ.
Rozumiem, že nejaký systém v tom je, len teda zatiaľ niektoré veci ani neboli nájdené, čiže hľadať ten systém je veľmi ťažké. Dobre.
A mne sa veľmi páči, to by povedal David Rowe, ktorý bohužiaľ pred necelým rokom zomrel. A on bol skôr matematik, by som povedal, ako fyzik, ale dosť sa teda zaoberal teóriou jadier. A on mi hovoril, že on si myslí, že je to pomerne jednoduchá štruktúra, ale ešte sme neprišli na tú fintu.
Dobre, ďakujem.
To nebude také zložité, len sme na to ešte neprišli.
Rozumiem, že ešte je málo kúskov tej skladačky, aby sa objavil ten tvar.
Málo dát.
Málo dát. Ďakujem.
Mohol by som sa ešte spýtať?
Áno.
Mňa by zaujímal, tam boli také...
Kto sa pýta, treba povedať.
Kamil Tokár z OKFS. A ja by som sa chcel spýtať, tam boli také diagramy tvárov jadier a zaujímalo by ma, že pri tých jednotlivých excitačných stavoch vyzeralo to ako nejaké elipsoidy alebo tak. Čo reprezentujú tieto objekty? Je to nejaká konfigurácia alebo distribúcia nukleónov v jadre, alebo je to nejaká interpretácia nejakých účinných prierezov tých stavov?
To je dobrá otázka, že či sa tu naozaj bavíme o geometrickom tvare, pravdepodobne nie. Bavíme sa teda o kvadrupólovom momente.
Čiže to je objekt, ktorý vykazuje nejaký kvadrupol alebo oktupol, alebo...
Ale či naozaj, my to kreslíme geometricky, ale či naozaj sa tu bavíme o... Aj keď sú v podstate merania rozloženia náboja v jadrách a tie ukazujú, že tie deformované jadrá ho majú väčší, ten polomer náboja. Že tým, že ono je deformované, ale nie sú tie experimenty polarizované alebo orientované, takže ono sa, keď je to jadro tvaru rugbyovej lopty, tak tie experimenty tohto typu ukazujú, ako keby boli veľké tie jadrá. A ono sa to napríklad prejaví aj v atómovom obale, že tie atómové prechody sú iné potom, ale nie dostatočne iné na to, aby to nejak zásadne zmenilo chémiu. Ono to nemá vplyv na tú valenčnú vrstvu, ale niekde dolu sa to dá vidieť a tak sa merajú polomery náboja.
Mohol by som ja k tomu povedať ešte? Tak tá deformácia, ona sa dá popísať vlastne tým, že sa podľa vlnovej funkcie určí rozloženie hustoty v jadre, čiže vlastne aj ten kvadrupolový moment. A teda tá hustota potom vychádza deformovaná. Lenže to musíme hneď od začiatku si určiť, že to jadro môže byť deformované a teda počítame potom minimum. A my sa teda, povedzme v Hard 3 Focus sa nachádzame v sústave spojenej s tým jadrom, lenže laboratórna sústava je iná, hej, čiže keď by sa to malo spočítať presne, tak sa musí urobiť obnovenie symetrie a tá realita je vlastne, že to jadro má superpozíciu rôznych orientácií toho deformovaného tvaru v priestore, hej, na základe momentu hybnosti. Celkovo ešte, keby som sa ku tej jadrovej teórii vyjadril, tak tam je veľa rôznych problémov. Jednak tá interakcia je silná, hej, čiže musí sa veľa aproximácií používať pri výpočtoch. A nie je jasné, že kedy akú aproximáciu a ako ich dať dohromady celkom dobre, aby sa dali popísať všetky javy, ktoré chceme vidieť. A čiže tá interakcia nie je úplne presne známa po ďalšom. A teda aj keď je známa, no tak už malé odchýlky v tých parametroch spôsobujú, povedzme to, že minimum energetické sa nachádza niekde inde, takže tam je veľa problémov ďalej. Keď chceme všetky tie efekty zahrnúť ako deformáciu, rotácie, párovanie a tak je to dosť zložité z teoretického hľadiska. Čiže tam je veľa problémov v tej jadrovej fyzike, teda v tomto teórii.
Čiže v tých tvoroch je vlastne informácia o symetrii problému, o symetrii nejakého efektívneho potenciálu toho jadra.
No, čiže pomocou tých symetrií sa často dá aj tá symetria určuje tú klasifikáciu tých stavov, ako sme videli tie rôzne diagramy. Čiže tá symetria nám veľmi môže pomôcť v tom, aj vlastne tie modely sú na nej založené, že sa to dá nejak celé klasifikovať. Hoci tá interakcia nemusí byť ani celkom dobre známa potom.
Ďakujem.
Ak nemá nikto nejakú rozumnejšiu otázku, môžem ja jednu teda? Mário, ma tak teraz napadlo, keď ste hovorili, že čo je to vlastne symetria, že dá sa hovoriť niečo o distribúcii neutrónov v tom jadre, že také niečo sa dá merať v nejakom zmysle, alebo že či tie neutróny to nejakým spôsobom vždycky nezaokrúhlia. Naivná otázka, ale...
Dá sa aj neutrónu, teda nepružný rozptyl na jadre. A aj sa robia takéto experimenty, ktoré napríklad ukazujú to, že tie ťažké jadra majú ako keby takú šupku na povrchu, tvoria tie neutróny, že teda je tá nabitá časť a na povrchu je šupka.
A tá pre tieto nesymetrické je tiež nesymetrická, hej, ako keby, či...
Áno.
Ešte, ak môžem, opäť Tokár, Kamil. A chcel by som sa spýtať potom, ako je to s celkovým magnetickým momentom jadra v tých rôznych excitovaných stavov. Či to súvisí, určite to súvisí s celkovou konfiguráciou, ale či to súvisí s tou komplexnosťou tých vnútorných interakcií medzi tými nukleónmi v tých stavoch. Či je tam nejaký trend, alebo či existuje na to nejaký jednoznačný model popisu?
Podľa mňa existuje experimentálne minimum informácií o magnetických momentoch vzbudených stavov. Ak vôbec, ako sú pre základné stavy. Pretože tam sa to priamo dá merať pomocou laserovej spektroskopie. Ale teda otázka je, že či je vlastne rozdiel, či sú tie vzbudené stavy nejakým spôsobom iné.
Áno.
Takže ja si myslím, že pomerne minimum informácií existuje ako v stabilných jadrách. Určite je, ale platí tam podľa mňa to isté, čo v základnom stave. Že čo všetko má vplyv na tieto magnetické momenty. Ako to nie je celkom moja parketa, tieto magnetické momenty.
Rozumiem. Ďakujem.
Any other questions, comments? So if there are no questions, we can finish this session. And I would like invite you for the next, which will be in June. And I send invitation through email. I suppose it will be also on Zoom if the situation with COVID doesn't change. So please, you are invited. Thank you again, speaker, and also participants. Thank you.
Thank you. Goodbye.
Ďakujem, dovidenia.